December. That's why 12 months. Okay. So since I'm using just his laptop, it is very clear that whatever I'll do, you can also do it. I have no magic in my laptop. So basically, it's just the same command prompts that I'll be using. Right. So basically, see, the first thing is to understand where you are currently, right? So this is a terminal window that you see. As I told, this I'm now currently using Windows subsystem Linux. If you use Ubuntu system, that's far better. Or if you use Mac, you have a Unix system. So when you open a terminal, I'm assuming that I have nothing. I have not sourced the basrc file of OpenFOAM. So if I try to use OpenFOAM comments, it will not recognize. So the first thing is to check where you are particularly now, in which folder or what location of your partition of hard disks, etc. So if you don't know, to see that the path, present path, you could basically do pwd. This is the command to see the present path. It is showing that I am in the home directory, and within home directory, the folder it's home in, which is the user directory of this WSL or Windows Subsystem Linux, right? So this is not my installation directory. But here, so there is. If I try to see what is there are different folder, but I'm not within any OpenFOAM folder, so I'm not in any user, installation directory. Is that clear? So now I'm just going to my home directory just to clear all this. So if you do cd, which is called directory $home, it will basically take you to the home directory of your operating system, which is in this case is /home/home. All right. So if I do that, it goes. I'm just clearing everything off to avoid confusion. Okay. So I am in my home directory of the operating system. Here. So as I said, the first thing would be to source the basrc file, which is located in the etc folder of your installation directory. Now, in this case, a keyword has been used to source that file. And I will show you probably that where it is located. So if I go to yes, it will work. So what I did, I'll tell you what I did. I basically use a text editor to open the basrc file of the system. So it is not related to the OpenFOAM basrc. It's for this operating system. So I just want to check whether in this basrc file, the command of the alias to source, yes. So it is written or not. So you see the last line. Yes. So what does this mean? Instead of the source command, there is a dot, which is equivalent. So it says that it is sourcing the user leave OpenFOAM 2012 etc basrc. So, and this is written within the system basrc file. That's why whenever I basically turn on the operating system, the OpenFOAM window is automatically activated. I don't have to do it separately. So this is the best way of doing it at once so that you don't have to do another time. If you don't have this command written, you have to do every time. Instead of this dot, you could basically set the alias of some keyword to do this. Okay. So is it clear? Why I am able to use OpenFOAM? Because it is already sourcing the basrc file whenever we turn on the operating system. Right. So, and what command I use? There's nothing. Nano is a text editor like gedit. I'm just opening the basrc file of the system from the home directory. So now I have checked that my OpenFOAM environment is already activated. So I don't have to do anything else. I can directly use my OpenFOAM commands. So what is my first command? I told after activating the OpenFOAM environment is to check the namespace, right? So whether the namespace is working, which is FOAM, F-O-A-M. And if I type F-O-A-M just from anywhere, let's see where I'm going. So it is automatically taking me to the installation directory. That means, which means that your OpenFOAM environment is activated. Otherwise, it will say that foam command is not known or it's not found, whatever it is. Clear? So what is the other way of going to the installation directory? So let's go to the home again. Home means home folder of the system. And let's see again where we are. I'm again and /home. I don't know what is my installation directory. So one way is to use the foam command. The other way is to use my environment variable of OpenFOAM. So what was the environment variable that I told for the home directory? $wm_project_dir directory, right? So I can directly go there, cd all directories, $wm project directory. Okay, so you can see that I'm going to the same location, which is my installation directory of OpenFOAM. Is that clear? So now that I am within installation directory, let us first see what are the folders located within that, which I have already presented to you. And I can basically do ls, which is the list command. It shows it has the folders that I showed you in the presentation. So all wmake is a script which basically compiles all the C++ codes within OpenFOAM. Third party is a folder where all the third party libraries are located. B is the folder where the installation executables are located. Platforms, the linked files are located. Tutorial is the most important folder for now. We will see what are the tutorial we have. Now we have applications folder where all the solvers and utilities are located. We have etc where basrc is located. We have src where source codes are located. And wmake has the compilation command wmake. Any questions till now? So let us first see the solvers, right? So which solvers are available and which solvers should we choose for our problem? So we will go to from here call directory applications solver. Okay, and we will see what is there. So we can see that within that we have DNS, one category. We have acoustic, basic, combustion, compressible, discrete methods, etc. There are many things which I know very little, only in my field. So for us, important is, let's say, incompressible, where all the incompressible flow solvers are located. Multi-phase, where all the multi-phase flow solvers are located. Compressible, where compressible solvers are located, etc. Clear? So we know where our source codes are located for the solver. So for example, I want to see what are my incompressible flow solvers that I can use. So we can go to the incompressible folder and see what is there. So these are the options. We have icofoam, triple foam, simple foam, pisofoam, non-Newtonian icofoam, etc. Right? So all of these are different codes which solves a different, not different, it solves the same governing equation, incompressible Navier-Stokes equation, apart from non-Newtonian probably. Non-Newtonian also solves the same governing equation with a different viscosity model. But their CFD solution algorithms are different. Some uses piso scheme, some uses simple scheme, some uses simple scheme, and depending on whether you want to use steady solution, transient solution, etc., etc. Clear? So now you know where your codes are located. Now, can anybody tell me how does the C++ code file looks like? What is the extension of the file? No, basically, how many code files you need for a C++ code? The main code, which is .cpp or .c, right? And then you need another file. What is that? The header file. Okay, .h. So any C++ code should have the main code in .c and the header file, which contains all the declarations and definitions of your variables, etc. So if we go to any of these solver, let's say the easiest one, the IIT-ISM, I go and I see what does that contain. So you can see that it contains the same, the main code, which is IIT-ISM.c, and the header file, which is here called createfields.h. Okay, and we have a folder called make, which allows us to compile. So for example, the IIT-ISM code I take and I will make it another new solver called Chandan's IIT-ISM, right? And I would change the governing equation whatever I want to as per my need, and to make it available to the OpenFOAM environment, we have to recompile it. And for recompiling it, I will show you how to do that with time permits. We will use the wmake command. Okay, so the wmake utility allows us to recompile the code. Clear? So that is what all these solver structures look like. So that's it. Now we will see what are the tutorials we have, and we will try to take a basic tutorial and then do all the 3 steps: pre-processing, solution, and post-processing. In case value is there, you have that. Okay. Any questions? Okay, so what is the way of from this path to go to my tutorial folder? Either I go backward and go to the correct folder, or I use the alias of the environment variable, right? What is the environment variable for the tutorial folder? DUT is the alias, but the environmental variable is $foam_tutorial. Okay, but easily we can use just TQT, which is the alias for that path, and we will directly go to the tutorials folder. Okay, and if I see what are the tutorials available to us, it is according to the solvers they have categorized it. And for example, the incompressible tutorials uses the incompressible flow solvers, multi-phase tutorials uses the multi-phase flow solver, etc., etc. So let us go to incompressible and see what are the tutorials we have. So we have IIT-ISM. So again, these tutorials are also categorized according to the solver. So within IIT-ISM, whatever is there uses IIT-ISM. Understood? So if we want to learn the IIT-ISM, which is the basic incompressible Navier-Stokes equation solver, we will try to see what are the tutorials are there, and we see that we have a lead-driven cavity problem, the first benchmark problem, and we have another elbow problem, which if you remember, I showed you the tutorial wiki website, which has the first glimpses tutorial has these tutorials. Right, so this is the first tutorial you should do and understand all the different options, commands, and utilities that you can use with this solver. So as I said, next step, if we want to run this cavity tutorial, we should not try to compile it within this location, because this is my original installation location, which may not, where we may not have the administrator access. And the other thing is we do not want to temper the actual repository of the code, but we will try to copy this folder to my run folder or any other location where I'm comfortable in running. Okay. So for that, if we want to use the run folder, which is basically my user directory, I would first have to see whether the folder exists or not, whether I have created that folder or not. Otherwise, we have to create the folder first. So let us see by run, where do I go? What does it say? It says that it is saying that it is expecting a folder like that, but there is no such file or there, which means that I have not yet created that file, and I have to create that folder structure in this path, right? So to do that, I can actually do it. So for example, I copy this name, and you have to create the same name folder, otherwise it will not recognize. So does control C works here? And let's say I'm going to OpenFOAM. Yeah, so basically I have this folder already. Okay, but within that we do not have the run folder. So I have to just created the run folder. So mkdir, which is make directory run. Okay, so now because we have this run folder, I'll just reset everything and I'll go to home also. Okay, so I am again back in home, but now I'll try again giving the run command and it will take me to that folder. Is that clear? So I just created that folder. Okay, so now what I will do is I will copy that cavity tutorial from the tutorial to this folder and then we will try to run it. Here, so the command is cp. Okay, cp is the copy command and I want to copy from home, or wait, it's better to go. So I'll go to tutorial first and go to incompressible. I go for cavity. Then I will copy. -R is to copy the directory, if you don't know. And I will copy it to home run. It's copied. Okay. So if I now go to run folder, I will see that I have the cavity file. Is it clear? I did it fast because I just copied the cavity folder from tutorials to my run directory. And now you can recap from the first session that what are the files you are expecting here. Just the three folders: 0, constant, and system. Within 0, let us see quickly. I don't know whether you have the tree comment here. No, the tree comment is not there. Okay, so let us go 0. We have U and P where initial and boundary conditions are there. Then we will go to constant and see what is there. There is no polymers folder. Note that there is no polymers folder, which means that we have not done the meshing yet. Okay, there is no mesh file, so we cannot run the solver, run the case now. But there is a transport properties file, and if you want to know what is written in the transport properties, you just open it with a text editor, and you see that just one property is there which remains constant throughout the simulation is the kinematic viscosity. Clear? So the transport properties contains a constant kinematic viscosity of the fluid. Now we will see what is there in the system, right? So in the system we have block mesh, which is the dictionary file to create the mesh. We have decompose per dict if we want to run it in parallel. We have control dict. We have every schemes. We have every solution. PDL block mesh dict, just forget about it. It is another thing. I'm not going to explain with you now. So, do you have any confusion about any files of the folder? So, apart from PDL block mesh dict, you don't need it. So, I'm just removing it. Okay. So, now I have this thing here. So, that's it. So, I am now going back to my actual case folder. I'm resetting everything. And I'm seeing that I have 0 constant system, right? Now I have to do all the 3 stages. First stage is pre-processing. And pre-processing means I have to create the geometry and the mesh. And here in this case, because it's a very simple problem, we will do it by using block mesh. So block mesh is a meshing utility which already OpenFOAM has. And within the block mesh dict, if you open, you will see that the normal architecture, how to create mesh. First, you define the vertices, then you join the vertices by lines, then you join all the lines to create surface, then you basically mesh it one by one. First, you mesh the line, then you mesh the surface, then you mesh the volume. and you can decide whether you want to put gradient in the mesing, etc. etc. I think you all know these things. So to mesh it, the command that we will use is called block mesh. Okay. So you have to do it from the main folder, which is cavity. That's the tutorial folder. All right. So if I do it, it does it. It creates all the patches, everything, and it creates. It tells you basically what are the different patches. Also, I will tell you that. But it uses C. It says that it's creating block mesh from the system block mesh. So whatever you have directed in the block mesh, it just executes that and creates the mesh. Here, now my mesh is created, and I will go back to the constant folder just to check whether my polymesh folder exists or not. So now you can see that you have a polymesh folder, and within the polymesh folder, we have all the mesh informations such as edges, etc., etc. So let's see what is there. We have boundary, we have faces, neighbors, leveling cells, corners, points, etc. Now the important file here is the boundary, because you have to see what are the patches that you have named in the block mesh, right? So let us open this boundary file and see what are the names of the patches, right? So you can see here, I have total 3 patches, showing 3. One patch is moving wall, and the moving wall type is wall. So if the type is wall, you cannot apply any patch boundary condition in your 0 folder. So you have to make sure that the type of the creation of these patches are correct. Fixed wall is wall, and basically the front and back is empty because we are doing a 2D 2-dimensional simulation. Now please note that by default OpenFOAM is 3-dimensional, right? So it does simulation in a generic manner in 3 directions, but if you have to do 2-dimensional, you have to prescribe empty boundary conditions in the direction that you want to restrict the solution to be calculated. Okay, that's it. We have now created the mesh. Now we have to solve it. Now to do the solution, we have to first decide whether we want to solve it in serially or using parallel, right? So let us do first serially. That means we will use one processor only because it's a very small problem. For that, you just have to call the solver name. So if you are not sure what solver you are using here, where should you see this information? Where is the information about solver located? Control, right? So basically you go to then system, where I am. I am in within polymesh, so yeah. So I will go to system and do the control day. And with the first line, I will check whether my application, if I want to use another solver, I have to change here. Instead of IIT-ISM, you have to use PeopleFOAM or PeopleFOAM. And then you have to see all the numbers are correct or not, whether you want to change any settings, etc. For now, I'm not changing anything. Okay. So what do you expect here? That it will start at t equal to 0 and end at t equal to 0.5 with a delta t time step of 0.005. And what is the right interval? Right interval says that right control is time step and right interval is 20. That means every 20 time step, it will save the snapshot. So what will be the p-value at which it will save? So 20 times 0.005. So every 0.1 second, it will save the snapshot from 0 to 0.5. Okay. That's it. So I will just call IIT-ISM and it is showing some error. Now, can anybody tell me what the error says? I did it actually just to see if you can find out.
Because we are in the control link folder, that's why
Is control link the file or folder?
Yes, sir. Holding the file.
Yeah. So how we can be within control link folder? We are in the system. But whenever you are calling the solver or blockmess, you have to name tutorial. So I forgot to go back. So we'll just go back and then call this solver again. And it solves, and it just solves in milliseconds probably. And you can see the execution time, 0.1 millisecond. Right? Yeah.
Suppose that I need to change the solver for a particular problem. So after changing the name in that control dig file, whether I need to compile it first or just
If you use an existing, you don't need to compile. But if you make a new solver, you have to compile. Correct? So if you use PeopleFOAM, it already exists. So OpenFOAM knows it, so you don't have to compile. Okay, so now it is done. Now let me try to open ParaFOAM if it works. So ParaFOAM command is to call the post-processing unit, which is ParaView in this case, from the OpenFOAM environment itself. But sometimes it may load an older version of ParaView. Now, if you want to load the recent version you have installed, you can the other way is the best way to do is you create a file called touch. Touch is the command to create a text document. And you, for example, I'm doing res.foam. So the extension of the file, that blank text document has to be .foam, then ParaView can recognize it, that it's a ParaView file. Okay. Then I'm calling ParaView separately. I'm not calling ParaFOAM because it may load some older version. And this file, which is res.foam, result.foam, let's say, and it will load it. Okay, ParaView automatically load the file and open the window. Okay, so it again close. So now you can see that that file is there within the case folder, so which means that it can read all the solution files. And before that, before I load it in ParaView, let me show you another thing. I'm just canceling it. So I will, if I do ls, you will be able to see that now instead of along with zero constant and system, this file I just created, there are 5 other folders, which is 0.1, 0.2, 0.3, 0.4, 0.5. And those folder contains the snapshots that we gave in the control tick, that I want to save the snapshots of the solution at those time instances here. And ParaView actually is going to read that. So ParaView cannot read in between anything. So if you want to see what happens at 0.005, ParaView cannot do it because you don't have the data here. So you have to change your right control accordingly. Okay, so let's see what ParaView can show us. And half an hour is gone already. Right, so here what you do is this keep 0 time. Oh, you cannot see it. Yeah. So this is how ParaView window looks like, and it has already loaded my geometry, everything. But you see that it is not at t equal to 0 time. So what I'm doing is I am actually untoggle this keep 0 time and then applying and going back to 0. So you can see that time is showing 0 out of maximum is 5. So you have 5 time instances, right? And let me see the velocity. So can you now imagine what you have given in the 0 folder initially? So the internal field is all 0 value we have given. And in the boundary field, we have given all these 3 patches, which are fixed surfaces, we have given 0. But this is the only one which is moving. There we specify 100. That means 1 meter per second in the x direction. Here. So that's what it is showing at t equal to 0. Now, when I run just the next step of the solution, it solves all the grid points here and accordingly shows us the field variable of velocity in all the grid points. Now, if you want to see how my mesh looks like, you can do this one. Surface with gradient. So is a very coarse mesh uniform grid we have created where it has solved the Navier-Stokes equation. And I can change here from velocity to pressure, and I can look how the pressure distribution occurs. Now you can calculate vorticity, any other derived quantity, then you can visualize it.
This is the post.
Sorry?
This is the post.
This is the post-processing tool. Yeah, this is post-processing the data that you have got by solution. Yeah. So any questions? I'll spend half an hour and I've shown you the basics. I'll just move to the dynamic meshing then, if you don't have any questions. So have you observed the three stages: pre-processing, solution, post-processing? Now I have to mention that pre-processing block mesh is just your very basic tool to start with, but you can create very complex meshes in any third-party softwares like ANSYS meshing or ICM-CFD or point-wise, then you can import it in OpenFOAM. Similarly, you can use different third-party post-processing tools. Like you can import the solution of OpenFOAM to a third-party post-processing tool like TechPlot, and then can post-process it there.
I don't use this OpenFOAM, but I'm using another open source software for doing the CFD analysis. It is called the Open Telemat. Right? When I extract the BTK files, so my BTK file it comes at different times. So suppose I run a simulation for 4 hours and I save the results for every 15 minutes. So it will give me a BTK file for every time step that I have saved. So every 15 minutes there will be a BTK file. So is there a way that I can combine, like for example, I cannot get an animation like you did, right? For all the 5 time step you're getting the animation. So I don't get it because I have a single
You
file.
can easily get it, right? A Python script. You have the snapshots at every 15 physical or computational time, whatever. It must be computational time, right? So you save all the snapshots, just write 2 lines Python code, join them, and make it an animation. Make it a GIF. It's just 2 lines of code. Use Python to do it.
But does this ParaView?
ParaView can load BTK. Yes.
Yeah.
So if you want to load the BTK files here in ParaView, you can use the ParaView.
Because I want to do the time series analysis through ParaView. But since
Time series analysis.
But sir, in the other software, there is a time dependent problem. There is the time is given. But otherwise, this will be done in the steady state condition. Well,
Confused. He is talking about post processing. How do you go to steady state?
steady state, there time dependent problem. Time is given the 5 minutes, 5 seconds.
Yeah.
But the steady state condition.
Yeah, you just go to the last time step. That's it. And if you make sure that you have reached to that fully developed state of the flow, you don't need all the previous stages of the transit. You just need one snapshot. You don't need animation for steady state, unless you want to see how the transient phenomenon occurs.
Yeah, so my the question was this that for example, I want to do the time series analysis, right?
Time series analysis of what?
Let's say how at a point how the velocity field is varying.
So you want to take a probe here,
Yeah.
and you want to get the velocity value there, and want to plot the time history of it with time.
Exactly.
You can do it in ParaView. There is a filter called probe. You can choose the coordinate, and then you can run the animation of how the course evolves. Yes, in ParaView you can do it. So if you load your data in ParaView, you can. Can I give some water? Sorry, I just had to understand. Okay. So should I continue?
After the as you have said that for post processing, we can do TechPlot also. So in that case, sir, this extension, this code won't be used in the last, like ParaView space result or.
No, that comment loads ParaView. If you don't use ParaView, you don't need to do it.
Sir, if I don't want to use it in ParaView, so I won't use this code. So instead, you
That
have
is
to
not
export
a
that
comment.
what I.
Yeah, so you have to export it. There is a command called foam to BTK. If you do that, it will convert all your OpenFOAM time folders, the results into a BTK folder, and then you open your TechPlot and load as BTK. from Windows it can be done. It doesn't depend on operating system. If you can open your tech plot in any operating system, you can just do it. Okay, so I'm guessing that there are no more questions. So let's move to a bit more advanced thing, which is the main theme of this workshop, which is moving mesh or FSI things. So I'll just stop sharing from here. Thank you. So now that you basically understand the workflow of OpenFOAM and things like that, so I will basically, given I have 25 minutes, I am not going to show you the code folders and everything, but I'm just going to show you the methodologies that are available within OpenFOAM to actually simulate FSI problems or any rigid body motion problem also using different methodologies, right? So first we have to know what are dynamic meshes and why do we need dynamic meshes and what are the different type of methodology that we can use. All right. And this is, for example, an animation of one way of moving the mesh. So you can see a pitching airfoil is moving, and you can see that this is a unstructured mesh, but there is a region, circular region around the airfoil, which is actually moving with the airfoil, and it is morphing, which means that the cell volumes are also changing at some scale. Okay, like if you see at the intersection, we can basically define an inner zone and outer zone, and we can basically morph the mesh or deform the mesh using by solving a diffusion equation. So a Laplacian equation. All right. So which belongs to the class of the first problem, mesh morphing. So I will basically mostly concentrate on mesh morphing and overset mesh to give you a brief overview. Right. So again, I'm skipping this. So when you actually morph a mesh, particularly when you actually want to incorporate this dynamic meshing strategy, what changes do you see in your governing equation, right? So if you see the general scalar transport equation, we actually have to consider the relative velocity of the body and the grid velocity in the convective term of our momentum equation. Clear? Because my mesh is also moving, my body is also moving. I mean, not body is moving and mesh is moving due to that, but it is the flow velocity. So the relative velocity between the flow velocity and the grid velocity has to be considered. So that is how mainly we incorporate the effect of moving meshes. And this mesh motion, how we can achieve, as I told, we can deform the mesh, we can add or delete or remove new cells, we can slide the mesh, or we can use multiple disconnected meshes and use interpolations to actually transfer the field variables from one mesh to the another, which is basically the methodology of overset meshes. Right? So why dynamic meshes are useful? Dynamic meshes are useful for simulating prescribed body motion. For example, in the first example, you can see that a cylinder is moving with a very high amplitude and frequency, which is prescribed, which you can prescribe what should be your amplitude of vibration, what should be your frequency, etc., depending on all the non-dimensional parameters such as Reynolds number, Stewart number, etc. And the second example, you see that again a pitching airfoil similar to the previous one, but here it is with a different dynamic mesh motion. Can you see the difference between the first example? This example, you see the animation, okay, how the airfoil is pitching and how the mesh is moving. And then you go to this one and you see this animation, how the mesh is moving. I think it's difficult to visualize from the back, but do you get the difference? What do you think is the difference of the mesh motion? No, both are pitching, I think. I'm telling in the mesh, the way the mesh is moving, what difference do you see? In the first case, I told that the mesh was deformed, right? So the volumes of the cells were changing.
So it is kind of adapts to the.
So here also you have two different zones. One is inner zone, another is outer zone. But the inner circle or the rotary mesh is actually sliding over the outer mesh. So in this case, the mesh is not deformed. Okay, the mesh region, inner mesh region is sliding. And we have to use a particular boundary condition in this case, which is called arbitrary mesh interface, which actually in turn uses some interpolation, okay, to get it transfer the data. And in the third animation, you can see it's a droplet rising kind of animation. It can be anything. But what is the dynamic mesh motion? So as you see that as it is going with the interface of the droplet, the meshes are getting created or getting deleted. So this kind of mesh motion is called adaptive mesh refinement. Okay. So in this case, we are either adding new cells or removing the old cells to track the interface of the of the droplet. So in this case, this is the liquid-liquid interaction. Is it clear? So these are different mesh motion techniques. So what I was telling is we can use it to simulate precise body motion, rigid body motion, fluid structure interaction, or mesh refinement or unrefinement. Again, so this is more clear, I think. So this example shows you the simulation of flapping airfoils, which was my PhD topic, so it was an easier example for me. And so you can see that these two examples you already saw in the previous two things, right? The first one is the sliding mesh, where the inner region rotates, slides with the outer region. The second one is mesh morphing, where the cells are deforming. The third one, we have two different mesh components, and both these mesh components are actually disconnected. So they do not have any overlap or grid to grid connection. All right. And you can see that which is basically involves a lot of interpolation, so it reduces the accuracy. However, it allows us to do much more challenging simulations which is not possible through this at all, because due to the negative cell volume errors, our solution will diverge. However, even if the solution is inaccurate, our solution will never diverge. Okay. So we have to be carefully choosing the interpolation criteria to get more accurate results. But this technique is called overset method. All right. So I will quickly go through it. So this is not very important. The important thing is this. Now that you have actually seen all the case structure, if you want to include this dynamic mesh motion or moving mesh strategy, the only file or only dictionary file that you have to include in the constant folder is called dynamic mesh kit. Okay, where you have to use appropriate moving mesh libraries and all related codes, of course, which is already written. You don't have to write it from scratch unless you want to modify them. Yeah, so we'll see what are the different parameters for that. Okay, so I'm not showing you, but here also you can use this grep command, which I showed before. If you grep the dynamic every mesh.h, which is the main header file of the dynamic mesh libraries, you can see within the source code folder what are the different codes or libraries that uses dynamic every mesh.h. So that will give you an idea what are the different type of problem you can solve within OpenFOAM. So one is, for example, rigid body dynamics, 6 degrees of freedom rigid body motion. This basically is a coupled FSI calculation, and there are many more. Okay, so this is how you should search different capabilities within the OpenFOAM directory. Okay, so I think I don't have time to do that. You can do it yourself. You know what is your installation directory. You can go to the source code. Within the source code, as you have seen, there are multiple folders, but two folders is dynamic mesh, another is 6 degree of freedom motion. You can go within that and check what are the different library of codes are available. Okay? So take it as a kind of homework. Right, so this is important. I will spend a bit of time here that numerics for the dynamic mesh consideration. So some of you have asked me in the previous session that if you want to use a different solver or if you want to solve a different problem, do you need to change your solver setup or every scheme or every solution or not? And it is absolutely yes, because of course you cannot do it blindly. Otherwise, your code will diverge. So you have to tune it accordingly. So these are some tips and tricks. If you use dynamic mesh, what should be your consideration for your numerics, right? So as you can imagine that dynamic mesh problems are inherently unsteady problems. So they are more challenging compared to a steady problem. So particularly for mesh morphing method, when you change the volume of the mesh at every time step, and if you have very high amplitude and frequency, your skewness and non-orthogonalities keeps on changing with time, and also your local cell size gets the cell volume changes. So for all this, and particularly another problem is for adaptive mesh refinement, because you are making the mesh more and more refined for a particular scalar variable, which is like alpha water here. Your local CFL number keeps on changing, right? So for example, to account for that, you must use a kind of adaptive time stepping. So you cannot keep your fixed time step with a very high value, very coarse value. Your solution will diverge. Then it is always recommended to monitor the mesh quality while dealing with particularly morphing meshes, because at some point, some cells locally, for example, you are doing a flapping airfoil or pitching airfoil, the trailing edge is very tricky because the trailing edge is a very sharp joint in the mesh. So for that, to resolve that, some people what they do is they slightly round it. If you use a very sharp trailing edge, what will happen is when you pitch it with a very high amplitude, the local cells gets skewed and gets very much non-orthogonal. So for mesh morphing, that is a big problem. So your case will diverge. So you have to monitor it constantly. And of course, your order of accuracy and stability criterions have to be more stringent compared to your steady problems, such as the tolerance, number of characters in your piezo loop. They have to be accordingly tuned so that your solution remains stable. All right. And of course, you can imagine that they are more computationally extensive. It is very intuitive. Okay, so I will just directly go to the options. So when you try to simulate prescribed motion through mesh morphing, which is not FSI, you have actually two different options. One is you either can define or use the available functional form of the motion, such as a sine omega t or cosine motion or some ramp motion, which are very basic and can be defined through a closed form trajectory, right? And you have a closed form equation for that. So you can actually write the code or write a function, use it, and use appropriate mesh motion library, and coming to this in a while. So that is one way. But for example, I want to move a cylinder in a chaotic manner. I want to prescribe my own trajectory, which does not follow any particular function, right? So imaginary case. So even that also you can do through a tabular form. So you can actually input the translational and rotational motion coordinates of the body with as a function of time, and your body will undergo that particular prescribed motion. So these are the two ways. Now, when we try to do mesh morphing, as I told, even before we solve the Navier-Stokes equation, or just first we solve the Navier-Stokes equation, and as a result, in the next time step when the body is moving, we have to move the mass. Now, how do you think the mass is moving? It's not moving automatically. We have to solve another equation for it, right? So that is basically, we have to use another solver for mass motion method, which is nothing but it is solving a Laplacian equation. And depending on that motion solver, there are different type of Laplacian solver. One is, let's say, displacement Laplacian, there are velocity Laplacian, etc. And they also have a diffusivity function that in the example that you showed, that only the inner region are deforming, the outer region almost are static. So you can decide how you want to diffuse that morphing of the mass and how much distance you should deform the mass. So there are multiple diffusivity mass diffusion methods. So one is inverse distance, and you have to give the patch name or body name, which is basically the body patch which we want to move. So if I show you some animation, it will be clearer. But these are all different list of available functions in OpenFOAM for different mass motion solver, mass diffusivity methods, and different type of inbuilt functional motion. All right. So you can play with it. You can also check your mass motion even without solving the equation itself. If you don't want to solve for a long time solve the equation, you can use this solver, which is called move dynamic mesh. It will only solve your mesh motion equation and give you a feel that whether that is an appropriate mesh motion for your problem. Okay. Right. So this is an example that I am using an oscillating displacement, which is already a built-in function, as I told. I'm giving an amplitude of 040, that means 4 meters in the y direction, and I'm using an omega rotational frequency in radian per second. And yeah, so this is for paraview, it's a dummy value, you don't have to care about that. And when I actually give this function within dynamic mesh state, the essential change that we have to make in the zero folder is the boundary condition. So when we give the body patch name to be moving with this function, the boundary condition for that body has to be moving one velocity. So this is the inbuilt boundary condition for the moving body or the dynamic mesh motion. Here, so if you do that, include a dynamic mesh stick, but forget to do it, you will get error. It will not work because you have to give appropriate boundary condition to the moving body. Here, right? So this I've already explained. I will share this slide so that you can see it later. But this is basically the predefined function and how you move the mesh with different diffusivity coefficients. Yeah. So this is how the settings that I told you with 4 unit up and down oscillation and with an omega value, it looks like that, right? So you can see that the volume of the cells are changing with the diffusion. So it basically with the inverse distance function, it is solving the Laplacian equation and diffusing the mesh motion in the neighboring cells. Okay, and you can just keep an eye on that how these refinement zones are varying, because I will now show you another example of using a different diffusivity method. And you can see how differently it can be. Right. So this is again using the tabular function. So this first column is the time, second column is the linear motions, and the third column is the rotational. So if you want to give an arbitrary motion which does not have any closed form equation, you can generate the motion in MATLAB or Python and then include the table here. For that, your solid body motion function has to be changed. Instead of oscillatory rotating motion or anything like that, you have to use tabulated 6 degree of freedom motion. Clear? And this is actually the prescribed motion. So if you see here, what I have given is from 0, it is 0, 0, 0, and 0 to 1. At 1, it starts or vertically 2 units. At 2, it goes in the x direction also 2 unit. In 5, it goes negative. Now, if you can follow that table, this will look something like that. So it goes up, then side, then it moves back, kind of triangle in a triangular. So whatever you will mention there, it will do the same. Okay, so this cannot be given through any function. Yeah, this is important. So this is the same problem, but here I was using inverse distance and I changed the diffusivity to exponential function with a 0.6 exponent. And you can see how the definement region is moving. They both are different. Right? So there is no right or wrong here. So you have to choose an appropriate mesh deformation for your problem. And of course, any problem before going forward with it, you have to validate it with a trustable reference, right? So to check the accuracy of your solution. Is that clear? Okay, so this is actually, you can also do multiple cylinders here. So instead of multiple oscillating cylinders, so here you can see that I'm using the same displacement Laplacian, inverse distance diffusivity. I'm giving two patches, cylinder 1 and cylinder 2. So previously, so everything is fine, but I'm actually using two different patches in this case, and let's see how it looks like. And those are all the other options. Instead of inverse distance, we could use inverse volume, exponential, etc., etc. They all are solving a different diffusion equation. Okay, so there is a strong mathematical background behind it. So if you are really interested, you can go to the source code. Everything is open and can see what type of diffusion equation they are solving, basically. Right. So you can see that cylinder 1, I am giving in the dynamic mistake oscillating displacement 040, and cylinder 2, I am actually using 200, and with two different frequencies, right? So one is going up and down, one is going horizontally, just to make it visible. So these are two different scenarios. You can see how it is working. So the first case, both are going up and down with the phase. And in the second case, one is going up and down, another is going horizontally. So you can also do this. Here. But what is the challenge here? When these two bodies comes very close to each other, if you do not do your meshing appropriately, you will get negative cell volume error and your solution will diverge. So in those cases, to overcome those situations, we need overset kind of strategy. Clear? And this is a flapping airfoil, for example, tandem airfoil, how you can do it. You can actually use two different patches and use different kinematics. If you want to, you can study the effect of phase difference, effect of Cohen number, etc. So this is done by one of my undergrad students. Yes. Now we come to FSI. Any questions till now? I'll take 15 more minutes.
15 on 5.
Yeah.
Why inform the next speaker that we started?
Or I can stop. I mean, you will run down.
You can continue. Just message the next speaker that it will start at in a gap of 20 minutes. No? Oh, that will be better.
Okay, fine. I'll just finish it in 15 minutes.
Just inform.
So, yeah, okay. Quickly, any questions till now in the prescribed motion?
In the tabular form, does it assume there will be a linear interpolation? Right?
Yes. I mean, if you give a big gap between time, it just interpolates, which is not expected. Right. So the similar approach can be used for FSI calculation with the limited degrees of freedom, of course, not continuous flexibility. Here, what changes you have to make is that the motion solver will change to rigid body motion or 6 degree of freedom rigid body motion. There are two different solvers in OpenFOAM which can do it, where you have to mention I mean, I will show you one case directly. You have to mention all the things that I mentioned here, but apart from that, you have to use a structural solver which solves the spring mass damper system of the springs that the body is situated on, right? So you have to give the information of the mass of the structure, inertia of the structure, and spring constant damping, all the required information. And also you have to give an information of a structural time integration scheme which solves the structural equation in a weakly coupled fashion, right? So in this solver, you cannot do a strong coupling unless you modify the solver and include another correction loop. So this is a partitioned approach, weakly coupling method. In this case, you can see I have used a solver called symplectic, which you can use as Newmark beta also, or Rangaputta 4, whatever, any time integration scheme that you think will give you a better accuracy and work with this problem, you can use with that. So I will try to see if I can show you a case folder, but probably I can share a case folder with you. I don't have time to really go through the case folder because I will just try to cover the overset. Is that okay? So the main difference between a prescribed and this FSI case would be that the solver will be. So instead of dynamic FMAs, that library, meaning that you have to use a rigid body motion and 6 degree of freedom rigid body motion library. And apart from all the structural parameters, you have to use a structural solver, which will do the time integration of the oscillator equation and transfer the displacement value to the Navier-Stokes solver in a staggered manner. The thing that I explained yesterday. So this will be a partition weak coupling approach. So as I told yesterday that this solver will not work appropriately for a very small mass ratio. Okay, if you want to run this VIP problem for mass ratio 1, you won't get accurate result. All right. So the last thing that I want to cover quickly is the overset method. Now, in comparison to the mesh morphing method, overset method, as I explained, we have multiple component meshes, and each component mesh will overlay on the top of each other, but they will not be connected to each other. Okay, so they are all disconnected meshes, and you can do both prescribed as well as 6 degree of freedom or FSI cases with this method also. Okay, now the important aspect is that how do we transfer the results from one component mesh to another component mesh? It's entirely dependent on the interpolation method that we use. Now there are multiple different interpolation schemes, and every scheme has its own pros and cons. So you have to understand which one would be more accurate and which one would give you a better resolution of the flow even at the boundary. And to get one tip is to get good resolution of results is that in the different component meshes, you have to use the same cell size at the surface, at the overset surface. Now, for example, in this problem, the same problem of a VIV of a cylinder or a prescribedly moving cylinder, I am using 3 different mesh components. One mesh component contains the patch of the body, which will be moving. Another would be, let's say, refinement zone, which will be in the neighborhood of this. And another will be background Eulerian mesh, which will not do anything, which will just be as a static mesh. Now, the boundary of this mesh will be called as an overset boundary and will be also used as a boundary condition. And also in the second component boundary mesh equally will be overset. So these boundaries where actually interpolation happens from one component to the other has to be of the same size cells. So that is one way to reduce the interpolation errors, and it's very intuitive, right? And as I told that even if the solution will not be correct, but they can intersect each other. So even if your body comes and collides with each other, the solution at that point will be wrong, unphysical, but your solution will not diverge because they are all disconnected. And overset meshes can add numerical diffusion to the solution, and interpolation is non-conservative. So this numerically you all know. Yeah, I told that in the overset meshes, cell size close to overset patches should be similar to minimize the interpolation error. All right. So I'm just keeping this. The important part here is that when you assemble or merge all these different component meshes, you get three different type of cells or volume of cells. Okay. One is called hole. What are the cells of the hole? The hole cells are, let's say, within the cylinder. There is a hole in the primary mesh, right? Mesh component. But there will be cells in the second and the tertiary meshes where we do not want the solution. For example, here, when you mark this in here, there will be some cells, and here which correspond to the whole of this mesh, where we do not consider the solution to be physical. So those cells will be holes, and there will be some cells at the surface which are overset surfaces where the interpolation will occur. We will call that interpolated cells, and the rest of the cells will be calculated, where we will solve as usual the Navier-Stokes equation. Here, now the next information is where interpolation will occur. There will be two different type of cells. One would be called the donor cells, another would be called the acceptor cells. That means it is important to for the code to understand from which cell to which cell the interpolation will propagate. Right? Yeah, so the interpolated cells can be classified as acceptors which receive information and donors which send information. Now, as I told, the most important case for these overset cases is to consider an appropriate interpolation scheme. So we have three different interpolation schemes. Let's say cell volume weight, inverse distance, and least square, and they have varied accuracy levels, and they have their own pros and cons. So you have to basically choose the appropriate interpolation scheme which works better for your problem. Right? So this is important. And this is basically an example again that the prescribed motion I have already shown. Now, if we do that same FSI problem, instead of a mesh morphing, we can use overset method. You see that I do not have any restriction in terms of its kinematics. We can just give any kinematics, it can go any amplitude and frequency, there is no mesh deformation, it will never diverge. However, due to the acceleration, the interpolation schemes has to be more stringent. Otherwise, when basically it goes a sudden transition from one motion to another, it may not capture the flow field well, the transition well, and there can be discontinuity in the boundaries due to the errors coming from the interpolation. So even if it looks very lucrative, unless we really need it, I don't want to use overset method because it is always less accurate compared to the arbitrary Lagrangian Euler limit. And the 6 degree of freedom component is exactly same as I have shown you for the morphing method. So we need the structural parameters, mass ratio, inertia, everything, and then we need a structural solver to couple the structural displacement into Navier-Stokes equation. I can skip it, but this is an additional capability which has been recently developed by one of my colleagues, is that when your structure is moving, the benefit is that you don't have to make the full background very fine. You can make a refinement region where actually you are interested to capture the flow physics, and actually you can move that refinement region with your body. I mean, you can stitch that with your body, which is a very important feature for doing challenging simulation where your body can go anywhere, like the one I showed yesterday, when your seed can go anywhere in the effect of the gust. And you don't need to really use a very fine mesh because we are only considered on the vortices that is forming at the boundary of the body. Right, with that I will stop for the break and answer any questions if you have. Sorry, I have to rush, but time is limited.
The comparison using OpenFOAM, the overset method and the other regular methods.
Yes, I have.
Sample problem.
Yes, I have done for clapping airfoils.
Okay, and how good or bad is the error of the overset method?
So overset makes is less accurate compared to experiment. And the one major issue of overset mesh is the is resolving the resolution at the overset patch where the interpolation occurs. So if we are not careful enough in terms of interpolation technique or the cell size, there will be fringe, which is unphysical. So for a flapping airfoil problem, I will never use overset because my morphing mesh can do